Hi, everyone. Welcome to another Haskell study group. I'm your host, Ron Batum with Atlanta Functional Programming. Today, we're going to be continuing our discussion of applicative. As you recall, last time we were talking about the applicative type class, a type class that's available in Haskell in the prelude that provides a way for you to essentially combine the behaviors of a monoid, which has identity and a binary associative operator, and the characteristics of a functor, which provides you with such things like um, the a identity structure preservation operator that is composable. We've discussed some of the basics of the applicative and saw some examples along with discussing how the applicative actually is implemented or at least is derived in the case of lists. And we looked at some examples with the how interacts with specifically the maybe type as well as the either type. We'll further actually look into the maybe type today, um, as well as look at some more examples with the list applicative to understand it a little bit more deeply. And we're going to actually go through today, hopefully, some of the discussions on the um, laws associated with the applicative type because this is very important. The applicative laws is essentially something that you would end up probably encoding, just like we did with functor, into a series of property-based tests using quick check. So that way you could actually go in and check that your applicatives are appropriately preserving the laws and they actually are um, algebraically um, closed under the applicative type class. Um, to begin with, we're going to go ahead and go back to something that we talked about last time again. We ended last episode with this discussion on the monoid type class and its implementation, specifically for, say, something like pair, and the applicative on pair that is restricted on the first of the pair and then leaving the second. And remember, this is mainly because, again, in the case of monoid, we did not have to worry necessarily about um, some the the kindness of the monoid because by default, if you actually go look at the kind of monoid, you'll see that it is actually nothing more than a single kind of type, whereas with applicative, it is actually a sort of a higher kind of type, which I'll for and more specifically applicative when you're using monoid. Applicative on pair, you will end up seeing that this will become a higher kind of type, and it can't be actually implemented. Whereas if we went and said like kind of A, you will see that this is for some type variable A, it'll actually go ahead and be a single kind of type because we've now restricted it. The pair is what's actually determining the kindness of the actual type class instance. Um, Applicative is already defined on this. I'm just kind of doing a brief review of this, but the one thing to remember is when you're looking at other operators, whether it be in this case, we're looking at pair, but for a normal tuple up to three parameters like a triple, you do have something like this, where you end up having to restrict it on those types. Anytime you have these multiple higher kinded types, you're going to have to go ahead and make sure that when you're implementing applicative that the type variables that you're restricting on all actually support and preserve the operations that are defined in the monoid algebra. So A, B, and C must be monoids in order for applicative of the tuple of 4 variables restricted on the first 3 is going to be a valid applicative, right? Um, Monoid is a very distinctive property that is actually required for all of our applicatives. So you might be wondering why, say, either or the list is not defined as having a monoid type. Well, if we go and look at monoid itself, you could see that monoid is already defined on, say, the list, and as well as the, I think it is defined on either, but I think that either is only I think it's actually defined. It's only defined for functor for either. It's just not defined on restricted for either. Right. So we actually have this defined in. Oh, the top level type for either is going to actually be the one that's going to end up being the case that we need to worry about, because either E is going to be the restriction. E has to be the monoid. It has to be a monoid type, since we're not actually having to worry about. So when you're looking at these applicatives and seeing where they're restricted on, notice the restriction on the actual higher kinded type to determine where the monoid algebra needs to be preserved. So in this case, it needs to be preserved on A, whatever the either the right side definition is going to be part of the either, or if you're having an E, you can or a left side, you're going to have that restricted on the left side, and that has to be also monoidal. So the type variable that's being passed into either is what's determining what that type variable must be monoidal in order for the either type to be a valid applicative. Um, Let me just check one thing here. The kind of either is also, I think, higher kinded, right? Yeah. Okay. So let's start with more on maybe. So we've talked about maybe before. Just a reminder, maybe is uh, a kind that is some type, well, that can either be a nothing or just of a specific type. And we've also talked about a little bit on what is actually the maybe defined on. Specifically, we've at least talked about the maybe functor at some point. But up until now, we haven't actually um, talked about the specifics about other types. So although applicatives itself is monoidal, because that's their very definition, is going to be part of the laws that we're going to touch base on in a minute. Making assumptions on the implementations, as you saw earlier, is actually invalid, right? So that's kind of what I was trying to show here earlier. So if you look at, say, functor, we see that stuff is defined on some types, but on maybe. But if you look at monoid, like we did earlier, you can see that it's defined on some stuff, or it's not defined on other stuff. The laws for applicative can be, while they have to be monoidal and functorial, it does not necessarily mean that you're going to have a monoid instance or an instance, a type class instance for that given type for it to be monoidal, and a functor instance for it to be a functorial aspect. You could actually implement all of that as part of the implementation of the applicative. All right. In fact, in some cases in the prelude, the instances for monoid and applicative, if they do exist, aren't actually required to being equivalent. They don't necessarily have to have the same exact monoid of structure. And the functorial piece, the way it's implemented, how you implement fmap, may actually change the way the monoidal structure has to be created. So therefore, for some types, And I'm not talking about some types as SUM types. I'm saying there is a subset of types that actually may have this behavioral change, which means you can't necessarily trust that the applicative is going to necessarily behave exactly the way if monoid, functor, and applicative are all defined, the applicative may not necessarily behave exactly the same way as the functorial piece or the monoidal piece, if that makes sense for folks watching. Um, Again, anytime I'm giving something, if there's a particular question that is confusing, please let me know in the comments, in the YouTube comments, so that way I can make sure that I go back and kind of address some of those issues in a later episode. If not, provide responses in the YouTube comments. Um, so if you look at, let's see something here. Um, did I see monoid again? This is it's not a monoid. No, this is not what it is. Um, I maybe, I maybe monad is defined, applicative is defined, functor is defined, but it's not. Okay, so it's not actually defined on mono. So how might we actually define a a monoid instance on a maybe type? Okay, because right now we've seen maybe being available here. Um, you can actually see here that the monoid is actually defined it here as requiring that the underlying thing is a semigroup here, right? Um, the way they define the monoid for maybe is going to actually determine how we might define the applicative actually. Um, so let's take a look at that. So unfortunately, since we can't actually necessarily look at the monoid in our REPL, the implementation here, we can kind of show how this is addressed. The book gave a very nice section explanation here in section 17.4 when we talked about when it was talking about applicative functors being monoidal functors to kind of illustrate this. So you might have a monoid A has a type constraint. Remember, the internal type has to be also monoidal, especially if later on we're going to have an applicative that's going to be defined so that FMAP can actually uh, be applied there and still, underneath it can make sure that that thing is also monoidal. Um, you can, so if you actually look at the definition of this guy, okay, you might have two things. Remember, when we define monoid, we have to define mempty and mappend at the bare minimum. Mempty is actually required. Mappend is usually what's required for when if you want to actually preserve certain identity properties, but it's the minimum that you need to define here for this type. So here we can actually go in and define empty as nothing because that's our identity. And if we're appending to nothing, we have to specify all the cases. Remember, where we're getting nothing. We also have to do this the other side, nothing m, the right identity. This is also m. And then if we're appending clearly a just a and adjust a prime, we end up getting just append a and a prime. All right. So this is very quickly the definition of our monoid. But how would the applicative work? Well, remember the applicative implementation requires us to actually go in and implement the following. It requires us to implement pure, which it lifts the type into the applicative world, and then we need to implement essentially something that's equivalent to our composition operator for functor, which is the the arrow, this star operator here, or the TIE fighter operator, as I realized the book actually started calling it. I think that's probably an appropriate definite way of defining it. So if we actually define this, one way the implementation can actually define this is the first thing is we need to define pure. Well, pure on the maybe type is just lifting a non-empty type into the maybe type, which just means that pure is just equivalent to just. So just is the type constructor, well, the data constructor for actually just constructing a maybe type. And now we can actually go ahead and define our fmap or our typhi operator definitions. So for the base case, obviously, we're going to be doing nothing composed with uh, anything, and that is usually nothing. And it's the same here. And remember, the reason why we're doing this is because this is essentially identity. And then what we are defining with the just cases. On the left-hand side, we have the functor that we're going to apply to a particular argument or the function, and we have the type of argument in on the right-hand side, and this is just equivalent to just fa. So if you look at this specific thing here, this is nothing more than our definition of uh, composition in the fmap sense, in the functor sense. It looks very similar, and you could see that the appending case looks very much like also the monoidal m-append case for just, as well as the m-append case or m-empty case of just nothing. Because remember, when we're appending m with nothing, it's as if we are starting with the non-empty version to begin with. And in this case, we're applying nothing to any argument. So of course we're going to get nothing. And if we're applying a function, any function or any functor to nothing, we're also going to get nothing, because nothing, you're not actually transforming anything, right? So this is kind of something that's important to just recognize when you are going through these type algebras, that I've been actually struggling as I've been kind of learning this myself. Um, these each bit each each algebra, whether it's the monoid algebra, the functor algebra, and now the applicative algebra, they have certain laws and certain behaviors that you must respect. And each algebra builds on top of the previous algebra in many respects. So if you remember, monoid isn't actually the beginning. Semigroup is actually the beginning, right? Semigroup is required, which is just nothing more than associativity. All right. Monoid builds on that and makes it associativity with identity. Then you have functor, which adds the concept of structure preservation and compositionality. And now with applicative, you are just basically saying that now your structure is preserved, it is compositional, it has identity, and it must be associative. So you've actually accumulated a lot of all the stuff that you've done before in order for this to work. This is why this concept of lifting is always talked about. This is why we talk about how do we append different applicatives together, how do we compose different applicatives together, and so forth. Okay, and we're going to see examples of this, particularly when we talk about the list of applicative next. We've already seen examples of the list applicative last time, but it's important to go and look at how this structure is actually derived. How is this applicative instance kind of implemented through some examples? Okay. Um, the one thing to first recognize is the types of the applicative when we're talking about the list applicative. All right. Here, when we just simply do this, um, recall that I think you can actually look at this in Google. If you look up how the list applicative is actually looked at on Google, you'll end up realizing that the rules for it is actually pretty straightforward. List applicative. Make sure I have in my list here. Um, here. Okay, so let's just go through this application. Just kind of walk through this. All right. Again, with list, with the applicative, we have to think about pure. Okay, just remember for applicative instances, we have to go and define pure, and we have to define the type I operator. All right, and that operator is actually called something specific, which is um, it's kind of like fmap, but it's also called. I think it's the apply operator if you really want to be more technical about it. So this is also called apply, right? So we're gonna need to define these two operators. In the case of list applicatives, we basically start with um, a a simple example. Given, let's say that we have some sort of list, all right? And we want to go and first some sort of type, and we want to first lift that into the list applicative. Well, obviously that means we have to define pure. So this is taking any type. It doesn't matter the constraints on the type right now. The underlying type can be. It doesn't have to have any constraints on it right now. But we're now lifting this type into our list. All right. And the easiest way to do this is just simply calling a, in the case of list, the empty list, the type constructor, right? So this is any um, construction on the list. This is actually, to be more precise, this is the left hand side. This is the type constructor for the list. So this is your signature here, for example. And you might say that, okay, for pure A, you can just say A, all right, and this will be just fine. Okay, in the simplest case, and you're lifting this guy up. How would you then define, say, our good friend apply then? Well, apply is actually doing two things. One, it needs a on the left-hand side, it needs a list, and on the right-hand side, it needs a list, okay? It's an infix operator, right? So on the left-hand side, it's a list of functions that we're going to be applying on a set of arguments, all right? So these functions will take essentially an A and return a B. Then what we'll do is we're going to go ahead and take a non-empty A and then return a non-empty B, right? And this implementation here is honestly very simple. You're going to have to write the kind of the base case here, and then which is just making sure you and I encourage you to go through this exercise yourselves. If you have, say, this and the empty set, obviously you're going to get empty, and then you can actually define a list of, say, um, let's say that it's F's and any and the empty list here, and then we can just say this is again a theoretical implementation here. So f's represent, our list of functions that we're going to apply on, and then, obviously the way that we split this up is we're going to go ahead, and if we do f and f's here, and then we have a x and x's, then what we're doing is we can just go ahead and apply and do a cons on f of x, and then we can do a cons on this, and then we can call the recursive call of the tie operator on the remaining f's and x's, and this will recursively call back into our apply operator to contact the next one and the next one and the next one. Now, I may not be getting all of this correctly because of the fact that, of course, there is one piece that I might be missing here, which is the place where, in the case of, say, if we're doing increment here, if we do +1 times 2, and we do star on 1, 2, 3, this is actually doing a concatenation at the end. Hold on, where is that? Oh, my apologies, I forgot the comma here. Okay. We're missing the M append here. So this piece here is just the map piece that I've just created. And then obviously what we need to really do is actually, I think I may have got this wrong. Hold on one second. This is going to be X's. And what we would do is we would do, actually, my apologies, we would do F map F because it needs to be functorial, right? So we do F map F on X's on the right hand side, right? And then we would use, and this is where the M append operator is required. You could do M append, and then you do F on X's. Right. This will actually do with the correct thing. So this here is the how it might be implemented. So what we've done is we took the head of the list, right? We took the head of the list, all right? And we've applied it, since we know that it should have a functorial structure where we can use its implementation of fmap on the right hand side, since we're assuming that they're both the same structure. And then we are calling mappend. Mappend is the monoidal piece of this thing, and we're mappending it to the rest of the application of what we're attempting to do. And then we'll keep going until we hit the base case of having an empty list and so forth. I'm going to pause here and see if there are questions.
Rom, should that be f map of f on x, then and then m append TIE fighter on the f's on the x's?
No, because X's is the whole list. If you look at what we did here, okay, in this example, this list, so which we're
Okay.
extracting, we're applying
Oh, okay,
each
I see it.
function on all the arguments.
I see it. So we're iterating through the functions, and then we're iterating, and for each of those, we're iterating across the subjects or the values.
Right,
Okay.
exactly.
Okay. Thank you.
So this is a very important, a good exercise, and you can actually see that now with this kind of structure, we can actually go in and do what we were doing before. You know, this is exactly the same thing as saying, let's say that we're doing powers of 2 here, 1, 2, 3. You could do that, or you could also do single list of power of 2, go this, call 1, 2, 3, and it's functionally equivalent, because again, the functorial structure is preserved in both cases, right? But the difference is in this first case, in the case of the single list, single element list of functions being applied. This is effectively an F map, and you're not actually leveraging the monoidal structure here of the list to actually applicative in order to actually go in and concatenate everything together. So if you have multiple lists, this is one way of actually dealing with that. Okay. Um, The one question I have here, and I think this is a good topic for discussion, is actually we're gonna touch base in this. So the one question for a lot of folks that are seeing this right now is this structure preserving operation, concatenation operation, looks very, very familiar to something that um, we may have encountered in other places. Well, if I understood this correctly, this applicative nature on the list, and I could be wrong, so correct me if I'm wrong in the comments, but I'm pretty sure that this is the basis for things like, say, flat map, because without the applicative nature, I don't think you can actually do a flat map, right? You can't do the kind of concatenation that you would normally do with a flat map without knowing that you have M append available to you, and you can't actually, what's the word, um, apply a function to create a list of lists without some sort of ability to actually call map on it directly. So you need both the fmap nature, which preserves the structure, and then the mapping due to compositionality and the ID, just all the functor laws, and you need the nature of applicative, which is the monoidal part, which is the associativity and the identity associated with that. So you can have some sort of equivalent to M append to be able to almost do a reduction of everything. Um, Second report. Thank you. Okay. Thank you. Okay. Now, this is all well and good, but we really need to kind of look at, some of the other operations that might be available. You're going to, you may see some weirdness like this. You could actually go ahead and say that this monoidal piece might, is this really kind of the case for the list applicative? You can actually break this stuff apart if you end up looking at things like how we might end up encountering, say, compositionality using the dollar operator with the applicative. Okay, so let's see an example of this. Okay, let's say that you want to create pairs of different lists. All right. Um, so this is kind of like a zip functionality, all right? You could think of this as a zip functionality that takes two lists and concatenate them, and that creates a pairs of them, all right? So you'll end up getting, say, if you have 1, 2, and 3, 4. Hold on, let me just go ahead and put a comment here. 1, 2, and 3, 4. This, if we're trying to create all the pairs, could be 1, 2, 1, 3, 1, 4, 2, 3, and 2, 4. Well, one way of creating this is just simply calling the pair operator, which is our comma operator here, along with our dollar sign on the list 1, 2 with um, 3, 4. All right. And you'll end up seeing the equivalent here. Now, to the keen eye, the dollar operator being written the way it is, you might be wondering, you might be curious as to why can't we do, say, something like this? Okay. If you attempt this, the reasons why you're going to get this is because the operator isn't actually being partially applied on the first list. All right. What's going to end up happening is this is determining the right to left applicativity of the actual function application. Okay. What that means is this here, this dollar sign. If you hit enter, first off, you're going to get an error. Okay. But the reason is because this is equivalent to this. It's as if you passed in this into the pair operator, which is clearly wrong, right? You're not going to get anything. First off, you're going to get an error on the side that the where we're expecting functions because they're all numerics, and then you have uh, other potential. You also have other issues related to the fact that applicativity on the pair is not going to actually work. That's what that first constraint, that type variable, non-type variable in the constraint uh, is complaining about. It's basically trying to look up the numeric type class for a function that takes an A and returns a B1, and that's obviously going to violate the signature for the applicative. So what this thing does is, and we can actually look through this here. My apologies. We can actually look at simply what does $12 create, right? If we just do this and say f's, I think we have our our functions essentially. If we look at the type of f's, you'll see that it's just a list of a that'll return a b that'll take an ab. All right, we've constrained each type of function that'll take in an a and then return a b. Right. And then what we've done is by calling this on 3.4, we've essentially went ahead and said, okay, type constructor 1 taken 3, type constructor 1 taken 4, and then so forth. And it will take the partially applied functions and complete the function application. All right. So that I don't know what to call this necessary. This caret uh this less than dollar sign greater than operator, all right, which is the operator for dealing with this applicative right to left application instead of left to right application. Um, this operator is required when you are trying to partially apply and create a series of functions using a type constructor on a series of data. So this is necessary in order for this all to work, and that's why this is written the way it is. All right. Um, and you can obviously see the partial evaluation of this again too. If that wasn't if this wasn't clear, basically this is applied to essentially kind of like think of 1 comma 2 comma applied to 3 4. And this here, unfortunately, it's actually really technically, to be more exact, um, comma 1. All right, because that's what that partial applied function is. If you do a 1 comma, I don't believe this this will actually work, but it might, because sometimes, yeah, this notation is clearly not going to work. But you could think of it basically like the following: this converts into essentially this function that's partially specialized on 1, the pair constructor partially specialized on 2, applied to 3 4. All right. So this here, this essentially becomes our 1 2 3 4. So you can see then before what it's evaluating, or what the shorthand is. There's another way of also dealing with this, because there's a function. This is so oft. This actually happens enough. This kind of notation for different kinds of operations, that the applicative class already provides a function in the name of lift a2 to actually go ahead and deal with this stuff, right? You have to first, I think I have to actually first import control.applicative in order for me to do this, but we'll see. Lift A2. Yeah, it's not available, so I have to do import, I think it's data about applicative. No, it's control. Control.applicative. Now, if we look at lift A2, you can see lift A2 requires F to be an applicative, and it'll take a function of 3 arguments and generate that. So how do we actually leverage this? And remember, you need to actually import control.applicative for this. You take in A2, all right, and you got all three, lift A, lift A2, and lift A3. We're looking at lift A2. We're going to go ahead and pass in our functor, which is our pair functor, all right? Pass in the initial arguments, 1, 2, second list that we're going to be part of it, 1, 3, 4, and you end up getting the same function, all right? This is the same kind of idea, all right? And this is for any binary operator. So if you end up using, say, lift A2 on, say, plus 1, 2, 3, 4, you'll end up creating um, uh, the addition for each of the operations. So 1 plus 3 is 4, 1 plus 4 is 5, 2 plus 3 is 5, and 2 plus 4 is 6, as you can see here. And you can see that this is equivalent, obviously, to what we saw earlier, which is this. Depending upon what your preference is, some people might prefer this application versus diffs. I don't know in what cases, for example, infix application would be more appropriate than lifting application, but I thought I'd at least mention it. There's, of course, lift A, which will simply take an A and a B and return an AB. And we can see that happening if we do, say, 1 plus, and then we pass in a list. And you can see that that's just simply nothing more than applying the function to each um, argument. It doesn't require multiple lists here. And you have A3, which allow you to connect up to 3 versions of the same structure to actually deal with it. The main point of this is the idea that you're able to go through each list and actually compute the individual pieces of the list. It'll look very much like, say, let me actually double check this. I don't believe you can actually have uneven lists here. It might complain. No, it actually does do it right. So in the case of lift A2, even lift A, but lift A2 illustrates this better than lift A. It's essentially computing the Cartesian product of the function application of the two lists together. So, and you could see this already in the case of uh, the pair operator. If we actually go in and call this on uneven list here, you could see that it's actually generating every pair. So 2 elements in the first one, 3 elements in the second one. Clearly, we're going to get 6 pairs out of this, and we'll end up seeing that. So this it is the Cartesian product of two of the function application between the left-hand side and the right-hand side. So, but this goes back to the monoidal nature and the functorial nature of the underlying structure. Uh, List structure itself that's giving us this possibility. And other structures that are monoidal and functorial will certainly do so as well. Most of the predefined functors and applicatives will behave this way, and the ones that you write should behave this way. And we'll see how to do that by first addressing the laws. I'm going to skip a couple of things here, just because I encourage you all to look up some of these things like the lookup function. I didn't really think the lookup function was really any more useful. Um, uh, like this is nothing more than a function that will um I think oh sorry, there we go. Lookup function will actually check to see given an A and a B, it will return um a B. So if you actually go do a lookup on, let's say, 3 on a list, say 3 and hello, it's going to go ahead and just return a maybe on the value of the lookup. Okay, so if you have a key value pair there, it will be very useful. Um, let's see here. Yeah, let's skip that piece there. And the so do we have yeah. Um remember seeing this. Just give me just 1 second here. Don't remember. Oh, okay. Um, Let us leverage this guy here. So if you want to test your functions and actually check to make sure things are, all great, you could just simply, without changing what you're doing, use just the identity of the underlying object to actually allow you to go through and define these operators and then play around with the applicative class. For this, inside data.functor, think this is in data.functor. I don't know if this also will work with uh, say um, applicatives, but we'll see how that works right now. There's this identity type in data.functor. So let's go ahead and add data.functor in our list here. And let's do the following. Let's say that we define a type called identity. This is kind of the example that was kind of in the book that I wasn't sure about here. Again, identity is not defined yet on anything here. You could theoretically say you're implementing these type signatures here, and not actually, you'll probably see something like this. And this here will actually go ahead and take an A and return a B. Again, this type shorthand is just a type alias. We've used this before. If we go in and actually take a look at it, it will actually address it the same way. Let me see something here. Is identity? Hmm, I thought identity was defined in. I looked this up on Google, and it says that it's available. It may not be available in what I was looking at earlier, but let's see. Identity. Um, yeah, if you want to play around with identity, you can go ahead and do that. I'm not gonna really do too much here. It looks like, unfortunately, it's not available in my version of GHCI. I'm not gonna go and figure out why that's the case. Just because I don't believe it is. Oh, there we go. there. I have to go and actually define. If I do that, now we actually have it. So let's see here. If I do type ID is identity, I do type ID, you'll see that ID is nothing more than a data structure. We can go ahead and define now, say, the apply operator on ID AB that will allow us to take an ID A and return ID B. And this does not need us to do anything because we haven't actually defined a type class instance for this, right? Um, why is this useful? Okay, because unfortunately I would have to show you how we define this particular applicative for this. The main thing is this allows things like, say, const um, uh, or us testing out certain functionalities uh, possible. So let's say that we have following the example in 17.4 here, where we're defining, actually I think it's 17.5. This is uh, something that I saw that we should go through. We have two lists, say, one is uh, 123, the other one is just 999, and we can just go ahead and call this on the x's with the y's here. And we get the same thing here. We're just going to return, since each const is actually going to be applied onto our x's. So we have const 1, const 2, const 3 being applied to each value 999, and then we'll get essentially 3 times 3, which is 9 values in our result set. The first 3 being 1, the second 3 being 2, second 3 being 3. And but another way of doing this and checking out some stuff is that we could create a function called, say, make ID defined on the identity operator, constant, call it, okay, and make ID or and make ID on the x's. And since identity itself is structure, okay, it is uh it doesn't, and more importantly, identity is defined, has a functorial structure and a monoidal structure. This together will preserve the identity of x's and apply them both together. So you'll end up getting identity of a list on the left-hand side and identity on the list on the right-hand side. And instead of flattening it like we did earlier, this is just going to go ahead and create this structure here for us. So this allows us to actually go ahead and, kind of verify the functions that we are defining will actually preserve that structure later on. Okay. Let's see here. All right. I'm going to skip the maybe applicative for a minute here. Go back to that later. I want to first touch base on the laws. Okay. So we're going to touch. I'm going to go a little bit outside of the kind of order in the book, just because I wanted to touch base on the laws first, since we've seen enough examples, but we haven't actually seen the laws. And I think this drives home some of the stuff that we've been talking about up until now. Okay. And it's very important that we have these laws available to us, because in a minute, I don't know, given the time, we might next time kind of write out our quick check rules and set these things up so that we can actually go ahead and work through them. So, um, so here Our applicative laws, just like our algebra, our laws for functor, laws for semigroup, laws for um, monoid, are essentially non they're not type checked at compile time. All right. They're not validated against your type class instance, but they are properties that conceptually your type has to hold in order for something to be a valid applicative. Otherwise, you're going to get runtime check errors. This is one of the reasons why you want to encode these into quick check properties to make sure that you are um, uh, 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 respecting them. So what are these properties? Well, first is identity. Clearly, we're going to get that. That is required because that's required for both monoid and for functor. But the other two is, and obviously composition is necessary too because this is coming from the functor rule too as well, and it will preserve some of the structure. Okay. Um, The third one is something of an interesting result, and that is there must be a homomorphism. Okay, and this requires a little bit of understanding of what a homomorphism is. Okay, if you've for the math people that are in the audience and who are probably watching this stream, um, thank you for joining, by the way. Um, You may recognize this term from modern algebra or abstract algebra, where a homomorphism is defined as essentially a mapping between two different algebraic structure. All right, but it isn't just a mapping. Okay, a mapping is usually another name for a function. It's a mapping that preserves structure. All right, this is a structure preserving mapping. All right. And it is the effect of applying a function embedded in one structure to a value embedded in another structure. All right. And it applies the function to this value without actually affecting the outside structure itself. All right. This is very important to recognize because if um uh this is obviously written, we need to make sure that uh that when we actually apply a function to the underlying value in some structure, that the structure is preserved. Otherwise, functorial, it's not a valid functor, let alone it's not a valid valid applicative. Okay, so I'm gonna mention the last property. I'm just going to show you how the Haskell properties actually look like in a minute. But I'm just making sure that you understand that this is actually what a homomorphism is. It's coming from that world, right? It's also coming from technically category theory because category theory has that weird, it's kind of a higher level extension of that. It's generalize it. But the modern algebra folks will definitely see and recognize that term. The last thing is interchange. Okay, so what is interchange? Okay, um, interchange requires first for us to look at the kind of law, but the idea is pretty simple. Um, it's basically trying to line up the the types, all right, and dealing with them with a composition, so that the application is accordingly well, the function application is accordingly executed and evaluated, right? I'm going to give you an example of this, but let me first write down the four laws, all right? So I named the laws what do they actually look like? Well, for identity, I think most of us know what this will look like. Identity requires us to first call pure, all right? And we're calling pure on ID, and we're applying ID on some value, and this should be equal to the value. That's identity, all right? Pure is lifting the function ID into the functorial structure of the right-hand side, and then we're applying that functorial structure to the value. So value is actually going to dictate what the lifting is actually going to go and do. Okay, what are we lifting the function into? Composition, again, I think it's a fairly obvious one too as well. Where again, we're lifting our composition operator, all right, applying it to the first function u, applying. Okay, so this is going to be just us applying pure on two different functions u, and then applying it to a set of v, and it's as if we basically did this, and we first applied the functorial structure of v into w, and taking that result and applying the pure lifted u set into those results. All right, that's kind of this. I think you can work out pretty straightforward, and we'll see some examples of this in a second here. Homomorphism actually is another one that once you see it, will become pretty obvious. And that is based on first lifting the function f again through uh, the pure operator, and then applying it to a pure x. All right, and we're basically lifting the lift of f and the lift of x is just putting them into the same functorial structure. We're assuming both sides aren't necessarily in the applicative world. Once we've lifted it, though, they're both in the same applicative world, and this should be the same as us lifting the application of the function to the value. All right. That's what homomorphism is. And again, you could clearly see because of us calling the pure, it is preserving the structure because the pure operating, its very definition is actually constructing um, the actual functorial structure, or it's assumed that the underlying pure lifting is going to be dealing with an underlying functor of some sort. Okay, or it preserves the functor behavior. Right. Um, Finally, interchange. This property is an important thing too as well. And I'm just going to end it here with this, and then we'll see this application next time. This is basically us taking potentially some, functorial list of functions. Okay, sorry, a functorial structure of functions. So it could be a list or whatever. And then we're applying it to a lifted set of values. And this is the same as taking pure, okay, calling $y, and then applying this to u. All right. What does this mean? Okay. The left-hand side is we are defining that the function is embedded in some sort of structure, right? That's what U is. We're assuming that it's embedded in some sort of structure, okay? It could be whatever, all right? You could call it on the maybe, whatever, all right? The um and we can actually see this. Let's say that we have um uh let me actually quit out of this so we can actually have a slightly increased, shortened list here. Let's say that we are, and hold on, I have to, of course, I gotta actually do this. I needed that. So let's say that we're just just taking a maybe, all right, which is a jest, all right, and we're applying it to pure two. The fact that we have u is our just, right, or maybe instance functor on the plus two. Okay, it's lifted. All right, pure two, since two is not actually lifted, pure is actually going to convert that into a just two, and then it'll go ahead and apply the function. Okay, on this. All right. So now, how is this uh going to preserve interchange? Well, this is the same as pure applied on $2 applied on just plus two. All right. Why is that? This $2 might look a little weird for folks looking at this, but remember what the dollar means. All right. The dollar operator is actually releasing the series of it's a partially applied dollar operator on the right hand side. Okay. And it's expecting a function to come in on the left hand side and apply it. All right. So what that $2 is doing is it's saying, okay, I am basically going to say this is the same as lifting. All right. It's lifting our partially applied uh, dollar operator. All right. And applying it to whatever set of functions on the left on the right hand side. So it's basically showing the commutativity nature of the fact that you could lift a right-handed partial application and it's as long as the uh, function that you're applying it to is going to act accordingly. And in this case, since dollar actually goes ahead and sets it up so that when we apply it, it's going to be the f, which in this case is plus two, is going to be applied to the left hand side of the dollar operator. Everything will get evaluated accordingly, and you can actually see the function application working as designed. This is essentially for folks really confused. All right, this lifting of $2 applied to just plus two is the same as just plus $2. All right, remember plus $2 sorry, is the same as doing plus two, and let's say that you wanted to apply to a series of parentheses. All right. That's what the same thing is. Okay, that dollar operator gets rid of a set of parentheses and allows you to go into applicativity. And since that itself is a operator, okay, will take an A and B and returns an A and returns a B. You can actually define it as on the left hand side and right hand sides because it is an infix operator. So technically, you can also do say double can also be added this ridiculous way, although this is already done this way. It's partially applied. Right? Although I don't know, yeah, you have to do it this way. Dollar plus two, and this will be the same. If you do double two, you'll get four. All right. The only reason why it doesn't work on what I showed earlier is because of the fact that dollar written the way I wrote it kind of expects you to partially apply on the right hand side, never on the left. Right? So if you do $2 here, this will expect you to pass in a plus two, or I could do a times three or whatever, and it'll work the same way. It'll apply to that function. So that's what interchange is. Since we're heading on 9:30, I'm just going to call it for tonight. Apologies for the slightly short um, discussion. We will finish up applicative next week, where we define our quick check stuff, talk about the zip list monoid, and we will finish off our using these applicative rules. We're gonna actually go through and dig into maybe applicative, just so that we could drive it home a little bit more. Are there questions from folks in our stream? Okay. If there aren't any questions, I wish you all a good evening. I'll see you all next week.